activation energy is related to reaction rate. It doesn't have anything with equilibrium constant. Intermediate formation is also not directly related. This is activation barrier, activation energy. So this is not related to that. Equilibrium constant is not stability of the product far away here. Reaction direction is about equilibrium. Stability of intermediate is not, we said. Stability of a product is nothing with this, but stability of reagent is related to this barrier. Because this energy is between this one to this transition state, right? Correct? So that's why stability of the reagent determines this the activation barrier. If reagent is too stable, it's more difficult to reaction go. If the reagent is less stable, then it can go faster. Okay, so that's the meaning of this reaction diagram. 이렇게 문제 있어? 심각한 표정이야. Okay, Gibbs free energy determines equilibrium constant. That's what the reaction direction means. And stability of intermediate is nothing with this. Reaction rate is this one. Transition state energy is also this one. 수업 끝나고 하시면 어떨까요? 우리 학원 그냥 거 있어서 12시 15분에 끝나는 12시 15분. Okay, Gibbs free energy is thermodynamic parameter. Okay, stability between this one to this one. This is thermodynamic parameter, and this is defined by energy difference here. And then this one is given by G0. Okay. And kinetic parameter is activation barrier here. This is the connection of the kinetic parameter. Kinetic means this is the speed. In chemical terms, rate, reaction rate. That's a kinetic. Designated with a double dagger. Double dagger is for this, right? This is for double dagger. This is for transition state. If you look at this, this means the transition state. Okay? This is ground state of reagent or product. There is no single dag in chemistry terms. Okay? Double dag or zero. Okay. Acid catalyst does not change energy state here and here. It changes the transition state possibly by changing the reaction pathways, maybe like this. So transition state can be changed, intermediate can be changed, and reaction pathway also can be changed. Sometimes there's one more reaction pathways like this, and this is not changing, but this is changing. Okay, so that's the catalyst functions. Okay, so this is the quick summary of last lecture. Okay, today we quickly summarize everything we have learned during this semester. Chapter 1 was structure and chemical bonding. Chemical bonding, before bonding, bonding is composed of electrons, non-nucleus. Right? So those electrons, the shape, atomic electron, orbital has s orbital, p orbital, and d orbital, like this shape. How was this discovered? The shape? It's the result by Schrödinger equation. That's a mathematical solution of the Schrödinger equation. So that's a wave function on space, spherical coordinate space. And if you solve those by applying boundary condition, then you can get this kind of the functions. And that's very well matching to experimental result too. So using this electron, we started to form bonding. And in this case, one electron and the other electron, they come together and they share to some the similar space. And then those space, when they come together, there is optimum the distance. And this is the nature of bonding. And the nature of bonding, simply we draw as just a single line, but actually that is more like electron is the surrounding together two nucleus, and this electron holding effect is making these two nucleus come together. So this is the nature of chemical bond. Especially this bond is covalent bonding. Sharing two electrons between these two atoms, and then those sharing is they are circulating together around these two atoms. That's the nature of the covalent bonding. Now, organic chemistry is centered for carbon. Carbon has a tetrahedral structure. Before that, carbon has a 4 bonding. So if it has a 4 bonding, two choices. Maybe one choice is on planar structure. So XY, XY, so that's one option. But space-wise, there may be a little more the stable structure to be this kind of a tetrahedral structure. But we don't have those kind of a tetrahedral structure in atomic orbital. So atomic orbital at the s orbital, the spherically symmetric, and pi orbital, x, y, g directions. So with this, it's difficult to make a tetrahedral structure. So maybe they come together and mix together, and then regenerate, recombined, rearranged, recombinated new orbital. And that orbital we call hybrid orbital, this kind of a remix of these three, and then redistribute on the space. So if you look at all together, x, y, g equivalent, and then this is the symmetric. So all together, if you arrange this again, this is spatially, this is symmetric too. Okay? All x, y, g direction is symmetric, and the distance of this is best matching on the space. So this is the explanation of combining of atomic orbital into molecular orbital in case of carbon, because it has a 4 bonding. Okay? So those 4 bonding is applied to single carbons and single bond. Now if there is a double bond, there's a little different situation comes. double bond is not equivalent to two bonds, right? Now we know that there is one strong bond in the middle that's similar to single bond. That's what we call sigma bond. And the other bond is perpendicular to this bond angle, a little loose of the new electron bonding. That bonding we call pi bond. So two non-equivalent bond is in double bond. And in this case, the combination is also p pi orbital does not participate in the hybridization. P orbital is still on the same axis, originally g axis. Only xy pi orbital is p orbital is participating with 1s. That's why this orbital is sp2. We call it 1s 2p. So this sp2 is on the same plane. And if you look at this from the top view, so this is a plane 120 degree, and this pi orbital is still on g-axis. Okay. So this g-axis of the pi electron is kind of an extra electron, right? Sigma bond, the electrons are tightly bound, they cannot move much, but this pi electron is relatively freer. That's why in the last lecture we have seen this pi electron can participate in electron donor as a nucleophile, because this is an extra electron and loosely bound. Okay? So that was sp2 and double bond. Triple bond case. So we can assume here then 1s and 1 pi, 1s and 1p orbital make this axis, and then the other two, py, pz, is independently exist. So two pi bond there, one sigma bond is there. In this case, it's only one direction, so this is one dimensional, so 180 degree. That's why if you draw, it's a triple bond. Not like this. If you draw like this is a highly strained, right? Highly stressed forms. You should look at. That should be 180 degree like this. So there was triple bond. Okay, so applying this, carbon is basically sp3 tetrahedral structure. If you apply this into the ammonia, ammonia has a one lone pair electron. You cannot see that because there is no atom here. But overall effect, they behave like sp3. And this lone pair electron is occupying one space over that sp3. A lone pair electron is a little bigger by volume. That's why they push this further down. Original, the carbon, the center, which has a 109 degree. So nitrogen has a little push down, so that becomes about 107 degree. Okay? So same analysis we can apply to water. Water has two lone pair electrons and push further down, and this is about this is the methanol. Water is 105 degree. Now the ammonia 107, methane 109, and water has a 105. If you have a little bulky one, then they push it back, so it goes back a little big one like this. Okay, water is 105. If you change this, the oxygen with the sulfur, sulfur has rather than the even bigger s orbital here. That's why their lone pair electron is a bigger space occupying. That's why they push them further. It's almost 92 degree further go down like this. Okay, so if you have an active group here, then there may be a little coming back. So that kind of a balance determine that angles. Okay, so standard number is 109 for carbon. So all of them we can say they are sp3 hybridization for that center molecules. Now for making those bonding, s orbital bonds to another s orbital like the H2 hydrogen, always two atomic orbital meets, then they generate two molecular orbital. Orbital number is also conserved. Two mixed together, one stabilized, one destabilized. And then sum up of this, or if it goes down maybe 3 kilocalorie per mole stable, then entire orbital may be the upper weight 3. So it's a sum up. The 3 minus 3 should be 0, should be same with this original. Okay. So similar things for the pi orbital. Pi orbital is also bonding orbital is here. Same character is attracted to each other. Opposite signal push each other. So this is unstable. This is stable. So this is the explanation of how atomic orbital recombine together and generate molecular figures. 동훈이 안 왔어? 동훈이 안 보이네? 어? 뭐라고? 연락이 안 돼? 언제부터? 오늘 아침. 무슨 얘기하고 그래? Okay, this is chapter 1. Any question for chapter 1? Okay, chapter 2. So in chapter 1, we thought about the atomic orbital, how we combine them to make a molecular orbital. Chapter 2, covalent binding, but it's a polar covalent binding, a little shifted to one side because of that different the electronegativity. Okay, not electron affinity or not ionization energy. Electronegativity determines which side the electron shift. So this makes this bond not fully covalent. This is partial covalent and polar covalent bond we say. If it is a fully ionic, like NaCl, then this kind of a bond we call ionic bond. And carbon-carbon, fully covalent bond, and polar covalent is in between somewhere. Okay? Sometimes it has a little stronger covalent bonding character. Sometimes it behaves like more ionic bond. So it's more easy to break heterolytically, right? If you cleave in the middle here, then that is related to dissociation energy. Dissociation energy tells about the two radical generations, and then breaking this up, this is more like ionization. That's what we have learned the last lecture, polar reactions. Right? Okay, resonance. In case of resonance, and only electron moves. There is no atom moves. Atom moves, even small movement is not included here. Only electron moves. And this electron moves is not real. This is just for explanation. That's what we can see in benzene. In benzene structure, we draw two resonance structure. Actually, it's not. It's a symmetric hexagonal structure somewhere in between, but that's more difficult to draw. That's why we chose this is next the worst option as kind of conveniency. So in this case too, this is not really double bond and single bond. Both of them should be 1.5 bond, and this negative charge is maybe half here, half here. That's a more realistic state. At one point, I pointed out that if you have a proton here, then is that resonance? If I put proton here, is that resonance? It's not resonance. That's equilibrium because hydrogen is moving in between two. Okay, there is a resonance only when they are fully negatively charged. Then they are symmetric here. Okay. 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 Now this is the resonance structure. In the last lecture, we said if electron is moving and pushing one side, and it should not stop here. If it stops in the middle, then it breaks the octet group. So once it is moving, then it's fully moved to the other side and finish up. So this is an intramolecular electron moving. Last time the polar reactions is intermolecular. Okay, intra means inside the nucleus, inside the molecule. That's intramolecular. And between molecules, that's intermolecular. That's important terms. Intramolecular, intermolecular. Okay. International is between nations. Intra-nation, you don't say much, but that's inside one nation. Okay. Intramolecular, intermolecular. In this case, it's intramolecular, right? Same molecule. Intramolecular or intermolecular. Anyway, if electron moves, then always it should satisfy octet group. That's why once this is moving, this is two electron moving, right? Two electron moved, then this should push it down and finish up those move. Okay, this kind of the resonance happens usually when it had 1 pi electron and 3 atom cases. So one double bond, and then is connected to another one. In this case, this is a negatively charged. Pi bond means, double bond means that it's a planar. Right? This is a planar. This lump electron, this lump electron, these two bonds, and this double bond, all 6 positions should be planar. That's sp2, correct? On there's an external one here, which has an extra electron. This electron on this plane, this extra electron donate from here and is moving, and then that double bond pi electron moving behind. So this generates resonance. This move down, double bond forming, and then this push up, negatively charged resonance. So anion works. Cation also works. If there is no electron, it's positively charged. Now electron movement is opposite. In anion case, this electron reach nucleophilic position. Okay, this one donate this electron and push it this way. If it's a cation, opposite way, pi electron donate, and then end result is this charge moved to this. Anion, cation both works. Even neutral, if it is a radical, still that works. Here, if the single electron, it can also, in this case, you should draw that arrow, single head arrow, right? Single head, like this. And here also single head, and single head. Then, and the result is double bond is shifting here, resistor here. Okay? We draw this. Again, this is resonance. That's not realistic ones. Okay? All of those cases, if it is an anion, it's more like anion, like this. If it's a cation, more like this. Radical, also, that radical character is spread out like this. This is the real situation. Okay? So this is the resonance structure we have studied here. Acid-base definition, there's several definitions, but Lewis definition covers everything. And this Lewis definition, you don't need to think about the proton generation, proton acceptor, only counting with the electron donating or accepting, right? Electron donating one we call base. Electron accepting one we call acid. So last lecture we said that we used a different term. Electron donating one, nucleophile. Electron acceptor one, electrophile. They have a very common features. And sometimes same material, they act as a nucleophile. Sometimes that behave as base. Okay, acid can behave as electrophile. We will see that examples later. But this acid base is totally different from oxidation reduction. That is the important part I said several times, so I hope you catch that part. Lewis acid, in a sense, each of those Lewis acid examples, they are almost matching with electrophile. Electron poor, and those are metal cations, and metal complex. Metal complex also metal cation character they have. That's why it is acid. How about the metal itself? Aluminum powder is an acid or base? Base. Aluminum powder is a reductant, right? It donates the electron permanently. It's not acid or base. It provides the electron permanently to the partner. That's a reductant. Metal ions, they are stable, and electron poor, they are acid. Powder, they have always a chance to become cation. That's a reductant. That's the difference between acid base and oxidation, reduction, oxidation, reductant. So Lewis base almost the same with the nucleophile. Lone pair electron of oxygen, lone pair electron of nitrogen, those are base and nucleophile. Okay. Also in this chapter we learned about the hydrogen bonding. Hydrogen bonding is a partially acid-base reactions. This the electron was donated with 2 proton and partially and then in equilibrium. So that's why water is not molecular collections. It's not like a collection of balls, collections of molecules. It's more like a network. Those protons are always exchangeable between different oxygens. It's a big network, 3-dimensional network. That's more realistic picture of water or ammonia. Okay? Hydrogen bonding forming ones, you need to have a proton source, H plus, and negatively charged the electronegative are the atoms, nitrogen, oxygen. Fluorine, does it form hydrogen bonding? Only in HF. If that protein is bound to carbon, it doesn't. That's too strongly bound to carbon. That's why it does not act as electron donating the partner. So usual hydrogen bonding forming one is the nitrogen, oxygen, and you need to have a proton source. Okay. Okay, that's a chapter 2. Any question for chapter 2? Chapter 3, alkane. Now we enter the real organic molecules. Carbon-based molecule which has hydrogen together. Okay. Carbon only cannot be the organic. Carbon only can be charcoal or diamond or with the oxygen CO or CO2. Those molecules we don't call organic molecules. So organic molecules should have a minimum carbon and hydrogen. And as additives, oxygen or nitrogen. So those molecules, so in this chapter we learned about the naming. So we are not going to cover everything, but at least from 1 to 10, above that forget about it. Up to 10, you need to be familiar with these numbers. Also, there was some naming of typical naming: methane, methyl, ethane, ethyl, propane, propyl, and with these abbreviations. Okay. Amyl pentyl we don't use much, but up to here, ME, ET, PL, PU is much. I wish you are familiar with this. Also, up to here, the butyl structures, there are the iso, sec, T, kind of the naming system here. Iso is fused together, so this is one word, no dash. Other than that, sec, tert, it's partially, so that's why you need to have this dash. Okay? Even the alphabetical ordering, iso is counting as alphabetical, the entity, but sec, tert you don't count. Okay? So that's fully fused, but these guys are still partially fused. Okay? This much you need to know. And general naming system, you need to figure out the longest one, alkyl chain, and then what is the substituted there, and then those positions. And then and the position is either alcohol or amine kind of thing. So we didn't learn that much. So most likely up to here is alkane, propane, butane, pentane. So that much we have learned in this chapter. So I can give you the name of the molecule, you draw it. Or I give you the structure and you give the name. Or I give you the wrong name, so you can draw the structure and fix those names. Okay? Give the proper name. Even though it's a wrong name, still we can draw the structure, right? After you draw the structure, original name has some problem, then you provide correct name. And in this chapter, we learned about the conformational changes. This conformational change happens through the rotation of the single bond. And that rotation barrier is 3 kilocalorie, 4 kilocalorie mole. That is in this temperature, 25 degrees. See, that activation barrier is not so high. That's why it can be rotatable. Kilojoule 4.2 kilojoule is 1 kilocalorie per mole. Okay? Kilojoule is unit of energy. Kilocalorie per mole is a unit of heat. So originally it was developed separately, but at one point, one genius realized that this is equivalent to the unit. So combined together, still use both of those units. So maybe most complicated one in this chapter we have learned is butane. So butane has anti-structure, most stable. Gauche has a second, not stable. These two are stable state. Globally minima or locally minima, and this is kind of intermediate, or maybe final stable one. And the other one, eclipsed one. So mathematically eclipsed one is most unstable. This is a transition state, not intermediate. Right? So by looking at that, you need to figure out what is the relationship of those. Okay, this is chapter 3. It's for alkane. So next one is cyclic alkane. Cyclic alkane, still there's no double bond. All single bonds, but is connected to each other. So molecular formula wise, one cyclic structure is equivalent to one double bond, right? Because the 2 electron, 2 proton, 2 hydrogen was removed. So that molecular formula wise, one alkene, one double bond is equivalent to one cyclic structure. So that's cyclic alkane. And once it forms a cyclic alkane, there's rotation is not fully allowed. In open cyclic alkane, the single bond could be rotatable. Double bond cannot. Right? And once it is formed this cyclic structure, now the rotation is not fully happening. That's why in double bond we can define cis and trans. They are stable. So it's not conformational isomer. Conformational isomer has the same meaning of the name as a conformer. Conformer is a conformational isomer which cannot be separatable under these conditions. But cis-trans, if you give those two forms we can isolate, they are real isomers. Cis-trans happens through double bond or in cyclic forms. Cyclic forms, now this is same direction, cis, opposite direction, trans. We have learned 3-membered ring, 4-membered ring, 5-membered ring, 6-membered ring. 3 and 4 is quite unstable. 5 is better, but still that's not fully stable. 6 is almost similar to open alkane because it can form this kind of chair conformation. I guarantee that. Would you draw pretty shape of chair conformation? How pretty it is will decide. 이쁘게 그려야 점수 잘 받을 거야. 요거 예쁘게 그려봐 하는 거 문제 낼 테니까 연습 많이 해와. Okay, so those are the chair conformations. Chair conformations, this is the most complicated one maybe. This one maybe, I will give you this graph and then you draw all those conformers in there. Or maybe just open the blank page, draw those conformational isomers of cyclohexane. 마지막 안 되겠어. 내가 그리기 귀찮으면 그냥 빈종이 주고 이거 그리려고 할게. Okay, so by looking at this the graph tells you that what is the relative amount of each isomer, conformer or isomer. So this is the equilibrium constant can be defined by this Gibbs free energy. And I may provide this one and I tell you by giving you this, then you can tell the relative amount of this form to this form. You can calculate. Okay? 교과서 문제를 다 풀어본 사람은 되게 그런 문제도 있었지. Okay, that kind of thing. And also the tertiary butyl is kind of almost anchoring to the one the ring flip structure. This one is much more stable than this one. And isopropyl or ethyl is not that much, but T-butyl has very strong effect to anchor this. Okay, so in cyclic structures, 1-2 relationship, 1-3 relationship, 1-4 relationship was a little different. Right? 1-2 relationship, 1-3 relationship, 1-4 relationship, 1-5 relationship, 1-6 relationship, 1-7 relationship, 1-8 relationship, 1-9 relationship, 1-10 relationship, 1-11 relationship, 1-12 relationship, 1-13 relationship, 1-14 relationship, 1-15 relationship, 1-16 relationship, 1-17 relationship, 1-18 relationship, 1-19 relationship, 1-20 relationship, 1-21 relationship, 1-22 relationship, 1-23 relationship, 1-24 relationship, 1-25 relationship, 1-26 relationship, 1-27 relationship, 1-28 relationship, 1-29 relationship, 1-30 relationship, 1-31 relationship, 1-32 relationship, 1-33 relationship, 1-34 relationship, 1-35 relationship seems like 1,3 is unique, and 1,2 and 1,4 has a similar. So one case is trans is more has equivalent, and sometimes if it's moving further, then trans also has a 2 axial, 2 equatorial. The stability was different. Okay, that relationship you need to study. And if it's fused together, if I draw this one, then I hope you can draw these forms. Okay, by looking at this, the transform and cis form, and which one is more stable, and how is that the conformation look like. So this one is more stable than this, right? This one has all equatorial, bigger one is equatorial, this one is one bigger one on axial. That's why that's less stable. Okay, in your textbook, there's only one the bicyclic structure, bridged structure like this. But in the class, we have a practice. If I give you molecular formula, there is a different cases of ring structure. We have practiced a little, right? 확실하지 않으면 수업 녹화한 거 다시 봐. 비우다 같이 그리면서 봤었어. 물어볼 가능성이 많아. Okay, this is chapter 4. Any question for alkane or cyclic alkane? Okay, stereochemistry. Carbon is a tetrahedral structure. That's why it has a chance to be chiral. So chiral molecule happens when the molecule has 4 different substituents on one carbon, and that carbon we call chirality center. Right? So if you have one chirality center, definitely you will have one enantiomer and the other enantiomer. Mirror image, but they are not superimposable. Superimposable means it's a 겹치는 거. Mirror image, but they cannot be overlapped perfectly. That's enantiomer. Physical property is almost the same. Melting point and everything is same except the optical rotation, right? But chiral material, it's not necessary for them. They have chirality center. My hand is chiral, but where is the chirality center? It's difficult to point out, right? And there's right-handed Godong, left-handed Godong. They are also chiral, but it's difficult to define which one is chirality center. We also had that cases in butane. Butane Gauche form, this Gauche form and this Gauche form. This two is chiral, but there is no chirality center. So in this case, so there are the symmetry axis to rotate this way or this way. So that's a little more complicated. We don't say much. But anyway, chirality center is not necessary condition for the materials to be chiral. Okay? Some of those chiral are the objects. They can be chiral even without the chirality center. And those difference is I explained with this optical rotation. For those optical rotation, the light should be, it cannot be any light. The light should be polarized light. Okay? It can be plane polarized or it can be circular polarized. This way or this way, either way, the light should be defined, polarized light. Then you can see the effect. So, configuration. So this chirality center, now we can say whether this is R configuration or S configuration. That is what we call configuration. Okay. That position, how is the structure? That's a configuration. So I hope you have practiced enough. You need to be able to give R or S form for each chirality center. Relationship of this enantiomer, diastereomer, epimer, usual compound. We handled it several times. You summarize yourself. And here, two chirality center, these are enantiomer to each other. There's an enantiomer-wise, there's only one enantiomer in the world. You are the real one. You have a mirror, and you have only one mirror image. And you cannot have more than one enantiomer. Now, if this enantiomer, then the other isomers should be diastereomer between these two and between these two. And diastereomers, they are different in physical chemical properties. This is a relationship of isomers. Definition of isomer, same molecular formula with a different properties. They can happen by structure. Constitutional means structural. Okay? Constitutional structural isomer here, and this is about the connections. Connection is the same, but the space position is different. That's what we call stereoisomer, three-dimensional isomer. And those examples here is enantiomer and diastereomer. 괜찮아? Enantiomer is a mirror image, and then diastereomer is a different property. In diastereomer, two forms. RS is different. Those the diastereomer the configurational isomer. So RS designation we said configuration, right? So this is configuration isomer. Cis trans is another type of isomer. Cis trans happens through double bond or cyclic structure. So this is the isomer, old isomer. Conformational isomer is maybe a little different, so maybe we need to put here conformational isomer separately. Conformational isomer is happening through this rotation, and another example was amine. Amine has lone pair electron on one side. It could be flip over, right? Originally it was an R form, but at room temperature it can be flip over to S form. It's a back and forth. That's why we cannot isolate them. Similar to butane case of the conformation isomer. Okay. Now during the reaction, whether the chirality center can be changed or not. That's we said several examples. In this case, reaction happens here. Ester formation, chirality center is here. And reaction happens here, methyl group added here. During these reactions, there is no chance of this chirality center has effect. This one we will study again later in detail. But anyway, this is the intro part for that. Okay, so this is a chirality and prochirality. Prochirality is two equivalent, two non-equivalent. So only by one-step reaction, whether if it is changing, then if it becomes chiral, then those positions we call prochiral. Prochirality can happen on the double bond side, C phase, brief rare phase. You can define those by rotation. You can define C and rare phase. Prochiral was a pro S, pro R. Okay, those are two definitions to figure out which is which. Prochirality, if they have chiral one nearby, those two prochiral centers are different. That's why it is important for chirality considerations. Okay, so this was stereochemistry. Any question for stereochemistry?
아까 전에 그 아이소머에 분류해서 컨포메이션 아이소머는 여기 따로 안 나오는.
These isomers are all defined and they do not change to each other. That's why it can be defined. But conformation isomer, if you have a butane, once you have seen this washer form, next moment it becomes this, it becomes this. Practically, it's not isolatable. That's why they didn't treat here. So that's why if you need to consider that, that should be different kind of isomer as a reference. 뭐라도 돼. 혹시 더 알고 싶으면 해석을 하세요. So those materials, in principle, they are the isomer, but it's not practically isolatable, so we don't count them as real isomer.
그러면 여기에 있는 것들은 물리적으로 분류가 가능하지만
Yes.
이제 컨퍼메이션은 아이소모의 경우에는 물리적으로 분리가 어려워서 과학적인 성질만으로 이제 그 비율이랑 존재형으로 파악할 수 있는 그런 느낌.
We can calculate those relative amount by measuring those the relative the energy state, or you can actually lower temperature down to very low temperature. Then the rotation is slowed down and they can be fixed. So in that the extreme conditions maybe it can be isolatable, but at room temperature it's difficult to isolate. Okay. Any question for stereochemistry? Okay, now organic reactions. So we just learned on Tuesday about these organic reactions. Organic reactions. Now there's the 4 different types of organic reactions. Addition reaction, adding something, and the reverse reaction of this is elimination reaction. Right? And third one was exchange reaction or substitution reaction. Or in the same molecule, rearrangement. So this rearrangement happened inside the molecule, right? Inside the molecule rearrangement, what do you call? Intramolecular rearrangement. Okay, that is what we say in the rearrangement reactions. Okay, so reaction type wise, the radical reaction and polar reaction. To do radical reaction, we need to break the bond in the middle. So for this, the weakest bond will be broken. That weakest, which is weaker, you can define that. You can determine that by dissociation energy, bond dissociation energy. CL bond was a half dissociation energy comparing to carbon-carbon. That's why if you have a mixture of this, and just heat it up or give light to the whole mixture, then this will be broken first. So that is kind of initiating material. So typical one is chlorine or bromine or hydrogen peroxide. So those can be dissociated, generate radicals. Generator or initiator. And then once radical is formed, then propagation can happen. This is very reactive, so you can attack this one, generate another radical, this radical regenerate this one, and then it's kind of a chain reaction. That's what we call propagation. After all the reagents are used up, then all radicals left over, then somehow they meet together and finish up. Radical is unstable, so once it is formed, then the stable molecule is formed and finish those reactions. So to do that, that means in the beginning you need to give a light or the hot temperature. Once the reaction started, you don't need to give it anymore because of this chain reaction, it automatically moves. And then it is ended up by removing all radical species. This reaction, I gave you this picture. This is almost like a breaking bond here. Usually that reaction requires a high energy and very harsh reaction conditions, which is not preferable. So to control those reactions in the laboratory scale at milder conditions may be better to attack here or here. So to do that, we need to shift the polarity from one side to the other. So that's the polar reactions. Polar covalent bonding is the subject of those polar the reaction, and then shifted electron, and especially if you wanted to make it even further shifted. If you have electron negative and electron positive, delta plus and delta minus, here we can add acid or base. By providing more electron here, or remove this electron, then this part becomes superpositive temporarily. Why temporarily? Because acid is a catalyst. Later it can leave. Tentatively it can disturb this polar bond, make it more polar. More polar is easier to break here. So that's the role of acid or base catalyst. Tentatively provide electron or depriving electron, and then disturbing those stable systems. So that's the role of acid-base catalyst. So this is the example, one of those example addition reaction. And now if you look at the molecules, rather than you memorize those the reaction cases, just try to look at the molecule and think, is that electron rich or electron poor? Chemical reactions happens always with electron rich one, with electron poor one. And by looking at that, with this, okay, this is electron poor part, this is electron rich part. And double bond is kind of electron rich one because it has an extra pi electron. Then this may act as nucleophile. This one may be nucleophile, this is electrophile together, combined together in one molecule. Then this nucleophile may attack this position, not this position. And this attack here and this push out, and it comes back. These are two-step reactions. And then during that reaction, sigma bond is not participating much. Here, pi bond act as nucleophile, electron donors. Same thing for benzene. Benzene has also pi electrons. Later we are going to learn that pi electron also can act as electron donating nucleophile. Pi bond or double bond, they can act as a nucleophile. And with this equilibrium constant, we can draw like this. And then K value wise is more than 1 is moving forward, less than 1 is moving backward, and then this can be defined by this free energy. And with these factors, now we can think whether this reaction is driven by enthalpy or entropy. Entropy wise, generally more species, that's more preferable. Entropy, positive number is more preferred. Enthalpy, negative number is more preferred. Negative means that's exothermic or endothermic. That's exothermic because negative, this is for the system. System energy is reduced. That means that much of energy is released to the outside. That's the direction of reaction moves. So that's exothermic. Exothermic is more preferred. And the entropy wise, increased entropy, this is 2 molecule becomes 1 molecule, entropy decreased. So that means still this reaction goes this way. That means this reaction is driven by enthalpy effect, not entropy effect. Okay? And by looking at this, the energy diagram, if its activation barrier is lower, now we can see G0, G double dagger. Double dagger means this is activation energy. G0 is comparing this ground state to energies. This is the exothermic fast reaction. Endothermic fast reaction. Exothermic slow reaction. Endothermic slow reaction. If you set up the reaction, 언젠가는 this reaction will happen, but you don't know until it can be finished by 6 p.m. when the class is over. Then you need to think how to accelerate this. What's your option? Maybe by putting catalyst. So, but if it is a multi-step, then we have seen this here. So everything was explained here. Activation energy here, and second activation energy here. If you look at this step, then this is activation energy. If you consider reverse reaction, then that activation energy should be this one, right? This reaction is reversible. It can go this way or this way. We just assumed we see this reaction goes this way, then activation energy should be this one. And rate determining step is also this one because this is bigger than this. But if you consider reverse reaction, then you should consider this one as activation energy because this should come back here and then come over. Okay? That is dependent on which side, which direction you look at the reactions. Okay? So the way you can accelerate the reaction is you utilize catalyst, enzyme catalyst or acid-basic catalyst or any other catalyst you can add. Okay, this is the last one. And we'll have the midterm exam next Tuesday, right here. before you go home, 저는 뭐 저거 평가하는 거 이렇게 질문 받는 동안 이거 작성해서